Okay, I'm going to talk about Lesbeque integral today. Lesbeque, spell like that. And of course, it's the extension of the Riemann integral that we learned in elementary calculus. Integral. So as you know, like what integral will do is basically trying to, let's say I have a function like that, and let's say I have an integral trying to integrate over this period, like this interval, like x1 up to x2 here. So what the integral does is trying to compute the area underneath this function. Let's say call this function fx. This function fx below this curve here. And basically the Riemann integral does is trying to partition this interval into very tiny strips. And instead of like summing through, computing the area under this curve, we're trying to just approximate this area as the sum of the areas of the strips. So therefore we have like the integral, let's say x1, x2, dx is approximate as, let's say I is from 0 to, let's say approximate x2 minus x1 over delta so many pieces, and f, let's say x1 plus I delta the I pieces. Let's say I try to take the value at the middle, so I plus delta over 2, and the area will be multiplied by delta, right? It's the height multiplied by the width. So, and that will be the approximate value, basically approximate area under the curve fx from x1 and x2. But if we allow also like the delta to take to 0, delta to be really, really small, then essentially the approximation will become equal. So that's kind of like what we learned about the more or less the definition of an integral. But the problem of Riemann integral is that it cannot tackle a function like the following. Let's consider a function gx that is equal to 0 when x is a rational number. So this is rational, and it's equal to 0 otherwise. So now for a function like this, let's say, of course, this function will be very spiky. Let me just try to sketch this. So it will be like lots of spikes. I do not draw it nicely, but all of these spikes should have the same level. It's 1 here, and of course within each of the spike there are many zeros also. So let's maybe zoom in like a region, like let's say I have a tiny delta, let's say call his delta here, and I zoom in to here. So no matter how tiny this delta, there's simply like many spikes here, and so therefore I cannot take any value. I cannot take any values of gx in this region to approximate. So I cannot say the area underneath this curve is equal to some value of gx multiplied by delta. So no matter how small the delta, this approximation won't be correct. So the rescue comes from the Lesbeque integral. So basically Lesbeque integral is trying to compute the area in a different way. So let me sketch another fx again. So again, let's say we want to compute, okay, this is not so, the shape is a little bit off, but it's okay. So we would like to compute the area underneath fx from x1 to x2 again. So rather than splitting this interval x1 to x2 into tiny strips, we're trying to partition this interval by as follows. So we'll consider, let's say, for particular f1 here, let's say I call this like f1. So for this f1, I want to see like look at the region that consider the sets that for the x that fx is equal to f1, and also and x is inside like x1 and x2. So and this is basically f1. So I have approximated f1 maybe is here. This area, this region here is again look like a strip, but as you can see it will be different because let's say if I have f2, let's say this is f2. Let me maybe use a different color. So f2, again do the similar stuff. F2 will be sorry, I shouldn't write f2. I mean f2. I'm only f1 and f2 I'll use here. Let's just call the set is here. I'm not going to name it, but the set will be simply the for the argument x that with fx is equal to f1 and fx equal to f2 and so on. So this set here will be like fx is equal to f2 and x is in x1 and x2, right? And so on and so forth. Then we consider for all the f's within this range, right? So we will consider basically, let me use another color. So for all the f's, I should consider all the f values here. Right. So therefore, like, the integral eventually can be approximated as for the Lesbeque integral will be equal to say f1 times the width of this set, right? Or like not I would say width of all the intervals contributing to this set. So mu is mu here is typically called measure. Is trying to, as I said, like going to measure the total width of intervals that contributing to this set here. So f x is equal to f1 and x is in x1 and x2. So and plus let's say f2 do the same thing. Very hard to write honestly. Mu x fx is equal to f2 and x is in x1 and x2, and so on and so forth. Sum over all the f values here, basically f3 values in this range here, and then that will be able to again approximate the areas underneath the function fx here between x1 and x2. So then, like with this Lesbeque integral, we can try to again find the integral or the area underneath this function gx here. Let's say we're interested to compute the area underneath gx from 0 to 1. So then using the Lesbeque integral, I'm trying to look at all the possible g values. In this case, it's simple, so I don't have two different values. So it's equal to 1 times the measure of the set that gx is equal to 1, and also like x is within 0 and 1. And of course, like gx is equal to 1 when like x is a rational number, so therefore this set here is actually just q and 0 to 1. the intersection of Q and the interval 0 to 1, plus 0 times mu, I don't know why I have this dot here, 0 times mu, oh, this pen is going crazy on the stylus, x g x is equal to 0 and x is in 0 to 1. And of course, mu is equal to 0 when, let me check. So Gx is equal to 0 when x is irrational. So that's basically that. But in any case, because it's multiplied by 0, I don't actually care about this term. So the question now is only like, what's the measure of the rational number between 0 and 1? We'll argue that the measure will be simply equal to 0, because if you think of the measure from 0 to 1, of course it's just the width from 0 to 1, so therefore it's just equal to 1, right? So but this is also equal to the measure. I mean, from 0 to 1, I can split it into the rational number, basically all the rational numbers between 0 and 1, and also all the irrational numbers. And we'll argue that there are simply many more irrational numbers than rational numbers, actually infinitely more, right, if you think of that. So therefore, the contribution of the irrational number alone should the measure for the irrational numbers between 0 to 1 should be already 1. So therefore, the left behind should be just 0. So therefore, eventually the integral between 0 and 1 for Gx will be simply equal to 0 in this case. And this is an introduction for Lesbeque integral, and it's commonly used in probability, more advanced probability courses, and in the context of so-called measure theory. But I hope this gives a kind of a simple introduction of Lesbeque integral. So thank you for listening.